Our topics are shear and moment equations and the diagrams associated with those equations. What you'll be able to do after this lecture is obtain the internal shear and moment throughout the entire length of a beam or member, and also create shear and moment diagrams from those equations. There are several things to discuss today. One is the sign convention that is used and employed that is associated with the shear and moment diagrams, but not with the coordinate system itself. An application for these concepts are beams that support wood, say at the local big box store. We don't want these arms to fail because they hold a significant amount of weight, and if that weight comes down, it can damage property or worse, people. So how do we know the beam won't fail? It's not enough to calculate the loads, the internal loads in the material at one point. No, we need to calculate the loads along the entire length of the beam to determine where the loads are largest, and from that decide whether or not the a given cross-section is adequate in order to support the load. Now, beams are exceedingly common and very often used in all types of structures. Technically, many things act as a beam that you may not think of as beams. For example, your kitchen counters can be looked at as beams. They're usually a constant cross-section extruded material where the material is pretty much uniform most of the time. The dimensions are usually much smaller in the cross-section versus the length of the beam. And the beams are often identified by their type or their cross-section or the type of load that they carry. So for example, a simply supported beam is a beam that has pivoting supports on either end of the beam. Whereas a cantilevered beam is fixed on one end, you see the middle beam here on the right or left-hand side, it's fixed to the wall where it cannot rotate relative to the wall and it cannot move up and down, but the opposite end on the right-hand side is free to float and can deflect. An overhang beam is a beam that has material that is loaded beyond a support that goes to ground. So you see how the overhanging beam has more material and the distributed load beyond point A going to the left. Another way that a beam may be identified is by its cross-section. So an I or T beam indicates the cross-sectional shape of the beam. There are also square or box beams that are either square or rectangular. And finally, even round sections can serve as a beam or a shaft. There is a sign convention that we employ when we talk about beams, because what we're interested in the beam are the loads within the beam, inside of the beam. In other words, if you just imagine a simple thing like a ruler or a pencil or something where you put force on either end and you're pulling on it, you're trying to pull it apart. Well, if you imagine a free body of just one side of this ruler, you realize there must be force inside because the two halves are not coming apart. So each half must be pulling on the other, and that is an internal load. In fact, that is an axial load. But it turns out axial loads usually do not cause failure, so often we will neglect those or not bother with them. Maybe we calculate it, and often that's a simple thing to analyze, but won't cause problems. But our sign convention for normal force or axial force is that if the normal force causes tension, then that is a positive normal force. So you see a section of beam shown in the top figure with two normal forces on either side. Well, those are not externally applied loads. That's the rest of the beam pulling on that center segment of the beam. Now, a lot of times we're not interested in a whole segment. We're only interested in, say, from a support out to a cut face. So you see a sort of a waved line on the left-hand side in the figure below, and then simply a normal force off to the right side cut face. Well, we could equally well look at the opposite side cut face and imagine the rest of the beam going off to the right with a normal force coming out. Those are all, what's shown there are all positive normal forces. But again, these axial forces are not usually ones that we are concerned with. But this introduces the idea that we could have a coordinate system, a positive-negative consideration that is different from the typical coordinate system. For example, if we were to plot a typical XY coordinate system, you might say, well, one of these normal forces is positive and one's negative because they point in opposite directions relative to the x coordinate, right? Well, that's not what we want to do. We want to think of these forces as being either tensile or compressive so we can be consistent, not so much related to an arbitrary coordinate system like an XY coordinate system. Now, we'll often still have XY coordinate systems, we'll still sum forces and moments according to that coordinate system, but when we make diagrams, our shear and moment diagrams, what we'll find is that we will want to consider the axis of that diagram and what is positive or negative. So it kind of makes sense that for tensile loads, they would be a positive type of load, and compressive loads would be negative. That way we can easily differentiate between the two. It becomes a little bit more confusing when we talk about shear and moment loads because you don't really see the reason yet for the sign convention we use, but here it is anyway. Imagine a free body. So now we're on the fourth diagram down. And we've got a segment of the beam in the center that we've cut out again. And you notice that we've got shear down on one side and up on the other. Well, what we say is that both of those shears on those two cut faces are positive because they tend to cause clockwise rotation of that body. Or if you look at the cut body, this third down on the left, what you'll notice is that we've got a downward facing shear on that cut face. Now, the rest of the body's not shown. There's a sort of wavy line indicating there's more to the body going out on that side of the body. But that shear force is a positive shear force on the cut face and in any shear diagram because it tends to cause clockwise rotation of the body. Similarly, the opposite face going to the right, third down, is a positive shear because it tends to cause clockwise rotation of that body. Now, when it comes to moments within the material, as long as the moment tends to cause a concave up shape of the segment or beam, whatever we're looking at, that is considered to be a positive moment. So a counterclockwise moment on the right-hand face and a clockwise moment on the left-hand face are both considered to be positive, not for the sake of an XY coordinate system, but for the sake of a moment diagram. So how do we come up with these shear moment diagrams? Well, we need to know the shear in the beam and the moment in the beam at every single point along the length of the beam. But that can be a little bit complicated, and let me explain why. So we're looking for V of x, the shear as a function of x position along the length of the beam, and the moment as a function of x, the length along the beam. Now the diagrams are just plots of that shear and how it varies along the length of the beam, and moment and how it varies along the length of the beam. Now it's really common to set it up the way you see here, where the free body diagram or a schematic representation of the beam and its loads are aligned with the shear and the moment diagram, so that if you're interested in the shear or the moment at any particular position, simply look straight down and you can read off the value of the shear and the moment. Now the shear and moment themselves are often discontinuous. It's not like we're going to have one single function along the entire length of the beam. Rather, we will have piecewise functions, functions that are valid along a particular length of the beam. So for example, from the beginning of the beam to point A is one function, from A to B is another, from B out to the rest of the length of the beam is yet another function for the shear and the moment in this case. So these are discontinuous, and each segment has to have its own set of equations. Now often we don't make a loading diagram like this for axial loads. We can. Another type of diagram you can make is a torque diagram, but usually we're dealing with two dimensions, and so we're not really interested in torque down the length of the beam. Sometimes that's added, but we won't do that in this case. So how do we go about plotting the shear and moment diagrams? Well, there's a whole step-by-step procedure here, and it'll make more sense when you see me use these in example problems. So I suggest as you watch my example problem videos, you keep track of this list, maybe print it out or have the slides up off to the side, and try to see where I am employing these step-by-step procedures to create shear and moment diagrams, and then it'll make a little bit more sense of what I'm doing. Now there's not just this slide, there's one more list of things that you should do in order to create these shear and moment diagrams. But once you get the hang of it, it's really not all that difficult. It's just a lot of work, that's all.